Okay, so hello everyone and welcome to another ICTS virtual string seminar. Today we are happy to have Nikhil from Penn State University with us, and he's going to tell us about the tensionless limit of chiral superstring integrants. Over to you, Nikhil.
Okay, yeah. Thanks a lot for the introduction and the invitation for this talk. So I'd like to spend maybe 50 minutes, if that's okay, to motivate why I think it's interesting to relate two theories which don't actually look very similar. Namely, on the one hand, I'll define everything soon. Namely, the ambitwistor string on the one hand, and the conventional RNS superstring on the other hand. And I'd like to sort of tie this in with other modern problems which I think are illuminated somewhat by this analysis. This talk is really based almost entirely on two articles that I put out in March. They're still under review. The first of these was a small letter which really just summarizes the longer article, where I've tried to study the RNS superstring integrand by expanding it in the string tension and then seeing what happens when we take an infinite tension limit. So the overall plan for this talk would be to uh, define the main tool which I'll be using in this, namely chiral splitting, and then discussing what happens when we, after chirally splitting the RNS superstring integrand, expand it primarily as a function of the string tension. Now, there are many ways to arrange an integrand in string theory, since there are other complicated analytic objects. What we will be interested in is expanding it in powers of the string tension, and then seeing what happens when we take it to zero. For a number of reasons, and mainly when we want to compare it to the ambitwistor string, it's most convenient to move to the domain where the ambitwistor string is naturally defined, but the superstring integrand is not naturally defined, namely the ordinary moduli space of or the moduli space of ordinary Riemann surfaces with n marked points. And this, as we will see, allows us to compare the answer with what we get with the ambitwistor string. So I'm sorry, was there a question?
No, it was just an announcement.
Sorry.
You can continue.
What is the ambitwistor string? I mean, just for introduction, the ambitwistor string is a worldsheet model proposed by Mason and Skinner, which consists of maps from the moduli space of genus G Riemann surfaces with n marked points into the space of complex null geodesics. Now, the ambitwistor string, although on the surface looks like a string theory, it's expected to really behave like a field theory, in the sense that you work with it like you work with any other string theory. You define vertex operators that are closed under a BRST charge. You find the correlation functions of these vertex operators, and then you integrate them over the moduli space. But it turns out, because of the specific properties of the BRST operator, that these integrands actually localize on a finite number of points. And when they localize on a finite number of points, the final answer turns out to be a field theory amplitude. This has been verified until Genus 2, and I believe a Genus 3 result will be coming out one of these days. Now, the ambitwistor string has a number of interesting properties, but primarily it is a chiral theory in the sense that it has left and right movers, which, unlike in the case of the ordinary superstring, are both holomorphic, and they are completely decoupled from one another. This means that any integrand in the ambitwistor string will actually consist of two parts coming from the two independently moving sectors of the theory. Now, incidentally, we have a very similar phenomenon like this in the conventional RNS superstring, which is known as chiral splitting, which was developed by D'Hoker and Phong back in the late 1980s. The question that I wanted to answer is whether these two formalisms are related somehow, namely that once you chirally split an integral in the superstring, is there a way to relate a holomorphic piece of that to a corresponding half integrand in the ambitwistor string? And it turns out that the specific domain in which the two are actually related is the tensionless limit. So I'll begin with some generalities, if that's okay, with to define how you actually construct scattering amplitudes in the superstring. I'll try to deal with all of this on a relatively high level, and if anyone wants, I can go into further details. So we're primarily going to be focused on computing scattering amplitudes for massless particles. I sort of abused terminology a bit there. We won't actually be doing any calculations of scattering amplitudes. Rather, we'll be looking at the integrands over the moduli space, because actually performing these integrals is usually too difficult. So suppose we want to compute the scattering amplitude for n massless states in type 2a or type 2b superstring theory. For our purposes, we'll only be dealing with even spin structures. So the distinction between type 2a and type 2b won't show up. Now, in the superstring, unlike in the case of the bosonic string or the ambitwistor string, the correct domain to work with is really the supermoduli space, not the ordinary moduli space, since fermions can run inside loops. So if one really wanted to compute a scattering amplitude, you would have to perform two distinct steps. The first of these is to actually compute the integrand, which itself is often very difficult, and then performing the full-fledged integral over the supermoduli space, which to my knowledge has not been done beyond the simplest cases, for even for the massless sector. So we schematically have an equation as given in the slide, where you take the integrand and you perform the integral over the supermoduli space. It should be thought of in a schematic sense, because there are actually subtleties in how you define the integration cycle, but this is sort of the broad overview. So as I alluded to before, it's not easy to perform calculations in RNS approach. If we restrict our attention to scattering amplitudes at genus 0 or genus 1, the supermoduli space is really defined in a very elementary way, starting from the ordinary moduli space. Then you take the ordinary moduli space and then you attach a fixed number of Grassmann variables associated to each external state, again restricting ourselves to even spin structure. And then all you have to do is integrate out these Grassmann variables, and what you have in the end is an integral that is an integrand that is perfectly well defined globally on the ordinary moduli space. And then if you're clever enough, you can perform the integral. Now, this is no longer true for genus 2 and above. Now, at least at genus 2, it was shown by D'Hoker and Phong in a series of very difficult papers back in the early 2000s that M2N can be constructed in an elementary way from the supermoduli space of genus 2, can be constructed in an elementary way from the ordinary moduli space of genus 2. But the projection that is required is a little complicated, because the most naive projection is not invariant under local supersymmetry transformations. But these integrals were not fully done, and even beyond these, at genus 3 and above, we have no idea how to project from the supermoduli space to ordinary moduli space. What we can do, however, is work on small neighborhoods, and within small neighborhoods, projections are always possible. So that's really the picture I want people to have, that we'll be thinking about integrands rather than integrals. And when we want to perform calculations, we'll descend from the supermoduli space to the ordinary moduli space in a manner that's very strictly local. And every statement I make in this presentation should be thought of as a point-wise statement, not as a statement that holds globally on the supermoduli or the ordinary moduli spaces.
Sorry, Nikhil, can I ask you a question?
Yeah.
So the statement you just made that you can always project, can you comment at genus 3? What happens? I thought that there was a whole portion of the moduli space which was singular, like a 5-dimensional portion, codimension 1.
You're talking about the spurious singularities that show up?
Some singularity that show up in the projection from the supermoduli space, the moduli space, but it's not like it's not the point, right. It's a whole space. So do you think it still holds in that case?
Yeah.
Your statements?
So what you're talking about, I think, correct me if I'm wrong, is that when you want to project, so at genus 3, you have to pick a set of picture changing operators to perform projection. And the picture changing operators can't be inserted anywhere, because you have a codimension 1 locus of singular points. And if you insert, they're singular points in the sense that if you insert spurious picture changing operators there, the scattering amplitude is no longer well defined. So even these local projections have to be done in a fashion where the locations of the PCOs depend on the moduli of these neighborhoods. So the neighborhood is parameterized by 3G minus 3 moduli and the mark points. And the choice of a picture changing operators as you move even on these open sets has to depend on these 3G minus 3 moduli. That's the sense in which you can pick a projection. But if you work on the global space, even that is not possible.
Okay, I get it. Thanks.
So the simplest prelude to chiral splitting is a genus zero. It's a little difficult to motivate things with genus zero amplitudes, mainly because things are so simple and generalizing these to higher genus is not possible. But I think this at least gives an illustrative picture of what's going on. So this is what I've given in this slide is a very schematic picture of how you compute scattering amplitudes in open and closed string theory. If you want to compute the scattering amplitude for n gluon scattering at genus zero, then it usually involves integrating a holomorphic function, which has a very specific pole structure when two punctures approach one another, multiplied by this universal Kober-Nielsen factor, integrated over the open string moduli space, which is just a simplex consisting of the n mark points, of n minus 3 mark points after you fix 3 of the points. But at genus zero, if you want to compute the scattering amplitude for closed states, closed massless states, then you have a holomorphic and an anti-holomorphic part. And the Kober-Nielsen factor itself is the squared modulus of the Kober-Nielsen factor in the open string case. The integrand, as a consequence, is just the squared amplitude of the integrand in the open string case. Now, this is the origin of the well-known KLT, Kawai-Lewin and Tai theorem that holds in string theory at genus zero. You can insert, in some sense, a complete set of states in between the holomorphic and anti-holomorphic part, consisting of a basis in the twisted cohomology of the underlying space, and then the amplitude factorizes into two parts. It factorizes into a product of two open string amplitudes convolved by the KLT kernel. So in this sense, a double copy structure is very clearly manifest at genus zero. The underlying question that I wanted to understand is, to what extent do these things generalize at higher genus, and can we use the same tools that we use at genus zero to understand double copy structures at higher genus? So suppose we want to understand chiral splitting beyond genus zero. Well, at genus zero, chiral splitting is very simple. You take the holomorphic piece of the open string integrand and you square it and you get the integrand for the closed string. But at higher genus, you can open up the paper by D'Hoker and Phong and you can see that the integrand is not, it's not easily resolved into holomorphic and anti-holomorphic pieces. What you can do, however, is if you're willing to introduce loop momenta into the theory and perform a global integration over these loop momentum variables, then this inability for the integrand to split into an holomorphic and anti-holomorphic piece can be bypassed. So once you perform the integral over the loop momenta, then you're back to something which is manifestly chirally split. But once you introduce loop momenta, you can show that if you take away the loop momentum integration, what you have remaining, the integrand which is integrated over the moduli space and the loop momenta, actually factors into holomorphic and anti-holomorphic piece. Loop momenta can be formally introduced by saying that the chiral fields, so this X here is actually a chiral field. It depends only on the holomorphic variable. And the full target space field is actually a sum of X as well as its anti-holomorphic counterpart. Saying that it has a monodromy around an A cycle, which gives you the loop momentum, is how you formally define them. So this way you get something which is known as the chiral integrand. Now, the chiral integrand is a quantity which, once you square, can be integrated over the loop momenta and then over the supermoduli space to give you the scattering amplitude for n massless states. Now, it contains two pieces. The first piece is the regular ghost piece, which I'm sure a lot of people are familiar with this. It's just the normal ghost partition function that the Berlinde brothers discovered, or they defined in a chirally split fashion. So I'll just allude to that later on. The part that's really non-trivial is the matter component, which depends on the external vertex operators. So it has this analytic structure. This slide is somewhat technical, so I can explain each piece in turn. Now, this first piece, which actually I've made a small mistake in this, I was supposed to multiply this by a gravitino field. That is basically the picture changing part, which contains all the information about what in the conventional formalism, that is the Friedman-Martinek-Schenker formalism, is known as the picture changing part. This part actually encodes the monodromies, which when you perform OPEs, this part gives you the correct shifting of the X field, and this is over the B cycle. I think there's a typo here, and these of course are the vertex operator pieces, which I've defined in terms of an auxiliary Grassmann field, which I think is conventional, so that I can put everything in an exponential and then isolate pieces effectively. So this is just a brief technical slide to explain the OPEs that I'll be using. The first is the standard OPE of 2 psi fields, and where delta denotes the spin structure, and the second is the conventional OPE between 2 holomorphic X fields. Note that all of these are completely holomorphic OPEs, which we are allowed to use effectively as a consequence of chiral splitting. And of course, this last the last equation basically describes the monodromies. So the omega i's are abelian differentials of the Riemann surface, which when you integrate them over an A cycle, or over the A cycle AI, suppose, you get 1, but if you integrate them over anything else, you'll get 0. So the pairing over this of some A cycle is just the identity matrix. So I'd like to now talk about what happens when you actually perform this calculation. For purpose of simplicity, I'm not giving all the details of the calculation, although I'm happy to get into it if there are questions later. So suppose, again, we're restricting all our attention to even spin structure. And when we do this, the chiral matter integrand takes this form. Now, chi PCO is just obtained by factorizing out this piece. When we do that, it's basically the equivalent of shifting the propagator of psi by some quantity. So you can perform all the integrals fairly easily once you factorize that component. It's relatively easy to see that in the limit of alpha prime goes to infinity, that part becomes identity. That part just becomes unity. Now the remainder can be organized in terms of alpha prime. The first part, which I've denoted by kn plus or minus, depending on what sign that you want to pick for the string tension, is proportional to alpha prime. And it's really just the plane wave component or the Kober-Nielsen factor that you have in the bosonic case, now generalized to higher loops. So people familiar with the ambitwistor string will see that, suppose we take the partial derivative of this with respect to one of the marked points, the factor that you bring down from the exponential is really just one of the scattering equations. So this is sort of secretly where the scattering equations, even in the ambitwistor string, comes from, because you have a Kober-Nielsen factor that shows up in the actual string, and the among the large other class of solutions, one particular part of the solutions that you get as a consequence of taking alpha prime goes to infinity is those that are defined by the scattering equations. Now, I'd like to emphasize that all of these, that this particular form, I'll define what H0, 0 looks like. Fortunately, we won't have to be worried about all the complicated things that come after that, since we'll be henceforth looking at the tensionless limit. But if you look at all of these at finite alpha prime, they're all really defined intrinsically on the supermoduli space. But if we want to make a comparison with the ambitwistor string, we'll have to reduce it to the ordinary moduli space. And so that's what I'd like to sort of look at now. So this is just a technical slide where I want to discuss what the form of H00 looks like and why this is sort of the critical piece of the integrand. So although it looks a little complicated, you'll notice that the gravitational field itself is Grassmann value. So each term in this expansion has degree 2 in the Grassmann variables, which means it is a bosonic function. But if we were to somehow say integrate over all of these Grassmann variables, the integral could be performed fairly easily since it's all quadratic, and we know how to perform Grassmann integrals which are quadratic, in a fairly simple way. One would know, for the simplest case, suppose we're looking at genus 0. Then if we're looking at genus 0, then all of these terms are 0. Because there is no gravitational field for 0 genus. And everyone will notice that this piece at 0 genus is really just what you would get for a tree level calculation. But once you perform the integral over the Grassmann variables theta I and the Grassmann variables theta tildes, what you get is just the Pfaffian that shows up in the ordinary CHY formalism. The same is true at genus 1 also, since for even spin structure, we don't have a gravitational field at genus 1. So already we're seeing that there is some agreement with the ambitwistor string. What we want to see is to what extent can we push this to all genus order. P-mu is a function that's well known in the field theory scattering amplitudes literature. The squared residue of this is set to 0 in the ambitwistor string formalism, and it shows up automatically in this. Yeah, is there a question? No. Okay. So if we want to now project down to MGN, and there are plenty of good reasons for doing this, because for a number of technical reasons, it's very hard to actually perform integrals over the supermoduli space. So one never really works on the supermoduli space. We only work on the ordinary moduli space. So if you want to say something sensible and something that can be compared to existing literature, then you really have to figure out a way to go to the ordinary moduli space. But as I alluded to before, this actually can't be done in the strictest sense, because the supermoduli space has a property known as non-projectedness, which Donaghy and Witten showed back in 2013 and 14. And in particular, it's not split. These two things have different meanings. Splitting mean when a supermanifold is split, you really mean that it can be derived in some very elementary fashion from some underlying bosonic manifold, which means you can just append a bunch of Grassmann coordinates, and moving from the super case to the bosonic case is done just by integrating over these odd variables. A projection means that you.
Sorry, can I ask a question?
Yeah.
I thought the abstraction was to a holomorphic projection rather than a smooth projection. Isn't that the case?
Yeah.
I thought a smooth projection always exists.
Yeah, you might be right. Yeah, I think that's true. Yeah, there's no holomorphic projection.
Okay,
right,
thanks.
Right. Sorry. So on the other hand, something is projected if you can patch together these split regions in a way that the maps between them are holomorphic. The problem is that there's no way of performing this holomorphic projection at high genus. And even if you have marked points, it's not entirely clear that a holomorphic projection exists once you go to high enough genus. But fortunately, if all we want to do is make pointwise statements on the moduli space, compare integrands that are defined on specific points, specific neighborhoods of the moduli space, then we can always perform projections from the supermoduli space. So now, since the genus 0 and genus 1 cases are so elementary and they're split basically identically, we'll restrict our attention to genus greater than or equal to 2. And here, for a small enough neighborhood, that is neighborhood parameterized by, say, 3G minus 3 bosonic moduli and the marked points, the odd directions are parameterized by the n Grassmann variables that accompany each of the marked points, as well as Grassmann variables, chi alpha, which I've denoted chi alpha, which are 2G minus 2 in number. And these allow you to locally expand the gravitino field as I've given in the slide. Now, as I pointed out before, the Z alphas here often have to be picked in a way that they basically depend smoothly on the moduli in these neighborhoods, because you're going to have to avoid a locus of the so-called spurious singularities. I can elaborate on that later, but they form a locus of codimension 1, and generically it's not possible to find a collection of these Z alphas which completely avoid the spurious singularities all over these throughout these neighborhoods. So you're going to have to avoid them somehow when you move in the moduli in these neighborhoods on the moduli space. Now, as long as you're working in these small neighborhoods, you're allowed to do a number of things which you cannot do globally. Firstly, you can expand your basis of superholomorphic.
Sorry, hello.
Yeah.
Hello. Hi. If I may, just ask a question, which is somewhat of a meta question, which is that I understand that you're working in this RNS formalism and trying to understand how something like ambitwistor string and so on and so forth would come about. But I'm trying to understand what is the why, in the sense that there are other ways of thinking about superstring where this, for example, pure spinner and so on. Wouldn't that be a better way to try to connect it with something like that, like ordinary moduli space? And why are we trying to do this in the RNS? So it's a kind of a meta question.
No. Yeah, I mean, it might be a better way of doing it. I don't know. So from my side, I don't understand pure spinner well enough to do calculations there. So I was working with what I had, but I perhaps pure spinner is a better way of doing this. But just judging from the structure of the supermoduli space at higher genus, I don't know to what extent you can make global statements even with pure spinner. But I mean, that's speculative. I can't be sure. It might actually be a better way of doing it. I don't know.
Okay. Thank you.
Yeah. So to do calculations of the ghost partition function, you're going to have to define a collection of Beltrami superdifferentials. And since we're working in small neighborhoods and we've been able to expand the gravitino field, we can define the Beltrami superdifferentials using 3G minus 3, the ordinary Beltrami differentials for the bosonic piece, as well as 2G minus 2 delta functions for the fermionic piece. And this is a fairly standard calculation. You can evaluate the ghost partition function this way. D'Hoker and Phong talk about this in their old papers, and I mean, there's nothing new there. This is how you make contact between the RNS formalism on super Riemann surfaces and ordinary Riemann surfaces. More interesting, however, is what happens when you project out these odd directions and move on to this small neighborhood in the ordinary moduli space. So to do that, of course, you have to perform 2n plus 2g minus 2 integrals over the auxiliary variables theta I tilde, of course, that you had from the beginning, over the Grassmann variables of the mark points given by theta I, as well as now you can integrate over the gravitino field since you're working in these small neighborhoods. Now, if I can go back to this particular form, you can see that one can actually guess what the form of this final answer is supposed to look like. The chi's are expanded in terms of chi alphas. So you have a sum over chi alpha, chi beta. And wherever the chi's are not quadratic, they appear only linearly along with some other Grassmann variable, which means that this really is just a normal Grassmann integral over a quadratic function. And we know what such functions are supposed to look like. They're just Pfaffians of the matrix that fuses, a row and a column of Grassmann variables. Now, I've written this schematically, where the matrix that takes these Grassmann variables and multiplies them. I've just denoted by psi gn. The expression for this is there in the ambitwistor string literature. It was defined, at least formally, for all genus by Gear and Monteiro back in 2018. And what I'd like to emphasize here is that in order to obtain the result that I've given on this slide, you're going to have to take two holomorphic pieces. So this is where you're going to have to do some something by hand, because the one fundamental difference I think that exists between the superstring and the ambitwistor string is that the ambitwistor string is manifestly holomorphic. Even if it is a chiral theory, in the sense that it has two separate sectors which actually behave qualitatively differently, the final correlation function is completely holomorphic. But this is not true in the superstring. So in order to make contact with the ambitwistor string, you're going to have to isolate the holomorphic contribution. And then, as it is done at tree level, you're going to have to take a left moving piece and a right moving piece. You're going to have to take a piece with two differing values of the string tension, which I guess you can say are opposite plane wave contributions, so that the Kobe-Nielsen factors manifestly cancel out. Once those cancel out, you're left with an expression that is the ambitwistor result, along with a number of alpha prime corrections. The specific form of the alpha prime corrections, I've not given them because they're fairly non-illuminating, and they're in a sense universal for genus 0 and genus 1. The genus 1 result looks just like the genus 0 result, which in turn is well known. But for genus 2 and above is just complicated, and at the moment I don't know what to do with it. But importantly, if you take the limit of infinite alpha prime, what you're left with is just the ambitwistor result. So in a sense, you can extract the ambitwistor string result directly from the superstring result once you perform chiral splitting and once you restrict yourself to the holomorphic sector. I'd like to emphasize that this is an all genus result. It is true pointwise. So if you have an integrand in the ambitwistor string defined at a point on the moduli space, for a corresponding point, for the corresponding supermoduli case, you can perform a projection in a neighborhood of that point and match the two integrands in this way. It is not a global result, and I would be very surprised if there was a global result linking these two. So I'll discuss why I think this result is interesting, and then try to make some speculative remarks about where I think it will be most useful. So,
can I ask a question before you move on to this? Or
yeah, sure.
So, are you gonna talk more about those alpha prime corrections?
No, I can if you want.
No.
But,
yeah. So I just because do you think they vanish in the setup you're talking about or not after integration?
After integration, you mean once you integrate over the scattering
and you GSO project?
No, they don't vanish. No.
Okay, so I'll ask you again in the discussion.
Yeah, I mean you can. Yeah, I think we have time. You can ask me if the question is relevant. I think you can ask me now.
Yeah, it's just that there is this statement that it's connected to this quantization ambiguity that Siegel also described, and in the old null string literature, people had observed that once you do this quantization twist or whatever you want to call it, although the theory still depends formally on alpha prime, the super version still formally depends on alpha prime, the results are like scattering amplitudes are equal to the supergravity scattering amplitude, irrespective of the value of alpha prime. So I was just wondering if those alpha prime corrections you're talking about could actually just drop out. Okay, so I mean, correct me if I'm wrong, but are you thinking about integrating the integral over the scattering equations, whether or not they vanish on that support? Over the moduli space. Because you don't really have scattering equations before you send alpha prime to infinity, right? You still have a moduli space integral to perform. No, I mean, you can just take this result and integrate it over the scattering equations. That's what you do in the ambitwistor string. Okay, yeah, if you have, yeah, you could do this.
Yeah,
Yes.
you can do this. And are you wondering if these alpha prime corrections vanish on the support of the scattering equations?
No, although that's a good question. I suppose they do vanish. Do they? I don't know.
I don't know. I mean, I was going to discuss them I was going to discuss this in the next slide.
Okay. No, I was asking a different question, but maybe we can come back to this.
Yeah, I'm sorry if I didn't answer your question.
No problem.
We can discuss
Thanks.
it. So
can I also ask a question maybe?
Yeah.
I was wondering, to what extent is it known whether the ambitwistor string actually makes sense beyond tree level, beyond sort of, yeah, I mean, within perturbation theory, but beyond the two loops? Or
are you asking about something fundamental like unitarity or something? Or
yeah. For example, do you expect unitarity to place some constraints on the high genus results or factorization? I mean, is it known whether, I mean, could you build the high genus ones from the lower genus ones?
I don't know. So there was a paper by David Skinner, and there was a paper by David Skinner and Kai Rohrig some time back, where they claim to have a construction by which you can fuse together two genus 0 results and get a genus 1 result. Attach another genus, a couple of genus 0 results to that, and build a genus 2 result, and so forth.
Okay. Will there be any obstructions to that procedure? Or
so from what I understand, this works wonderfully for genus 1, although it's very complicated since you have to perform you have to sum over Raman states in between, which is very difficult. But because, I mean, if you're really fusing together higher genus surfaces, if you're really fusing together these surfaces using these gluing operators, you're going to have to include all the internal states.
Yeah.
By hand. And remarkably, they did this for genus 1 using some old, all multiplicity results that people like Schlotterer found for Raman states.
Okay.
For genus 2, as far as I know, they were not able to do it conclusively. But I know that it's not been tried in a very serious sense, because this was before the two-loop result of Geyer and Monteiro. So they've not tested them yet. I know that the reduction, to the nodal Riemann surface result that the two of them found took quite a bit of effort at genus 0. And I believe they are currently working on this at genus 3. And I've heard, and they tell me it's much more complicated at genus 3.
So, I mean, let's say that in principle this is possible.
Yeah.
Would this mean that that one can construct a theory of quantum gravity without including an infinite number of fields?
This doesn't tell you anything about whether or not it's renormalizable. You're constructing the integrands, right?
Yeah, but I thought that only massless states propagate in the loops.
Yeah, I mean,
twistor, right?
So the conjecture is that maybe I didn't emphasize this in the beginning, but the conjecture is that the ambitwistor string gives you scattering amplitudes of type 2A supergravity. So it's, I think secretly the question you're trying to ask is it possible this way to make some statement about the renormalizability or the impossibility of that for type 2, type 2 supergravity? It might be. I mean, if one is clever enough to find, I believe people like Zwieber have 5-loop results now. So if you're clever enough to do these things at genus 5 and above, then maybe you can test those results. But
I see.
These results are formal in the sense that I don't think they can tell you something which about these questions that those kinds of unitarity, very serious unitarity based things cannot tell you or haven't told you already.
I see. And have constraints such as modular invariance been exploited? Or anyway, sorry, I shouldn't be. I don't want to interrupt the flow of your talk.
No. This is fine.
There's lots of interesting things to. But yeah.
Yeah, sure. I mean, maybe after the next slide we can discuss this more.
Okay. Thanks.
Can I just ask a question? It's a sort of a naive question. On the slide you have the statement that this does not tell us that the two theories are equivalent in the tensionless limit. But I was just wondering, I mean, how do you, and then about the two theories having different vacua, I mean, how do you really even define the type 2A, type 2B superstring in the tensionless limit for flat space? I didn't quite get what you were really getting at in the statement there.
Okay, so the two I've just put the statement about the vacua because I thought that would be more familiar to people. But I mean, it's relatively easy to see that the two theories are actually not equivalent in the tensionless limit. They're not even equivalent to at tree level. So suppose you have a scattering amplitude for n graviton scattering at tree level, and you take the limit of alpha prime goes to infinity. When you do this, the scattering amplitude does not localize only on the Gross-Mendel saddle points, namely the saddle points that come by imposing the scattering equations. You actually get a hierarchy of saddle points, which I believe, and somebody should correct me if I'm wrong, which are actually defined on the covering space of the moduli space, even at genus 0. And you have an infinite number of saddle points, which you have to then sum over. And you're left with a bunch of phase factors that don't show up in the, in the CHY formalism or the ambitwistor string. The equivalence is really at an integrand level, where you take a holomorphic piece and you take the square of the holomorphic piece and you do the squaring in a way that's consistent, then it matches the corresponding integrand in the ambitwistor string. This is not a statement about the equivalence of the two theories, because the naive alpha prime goes to infinity limit in the superstring is difficult to investigate even at genus 0, and to my knowledge has not been investigated above that.
Yeah, so that's why I wasn't very sure what you were comparing it with in some sense, because it's not very well defined. And I was just one. I mean, of course, when something is not very well defined on one side, you could try to make the other side as perhaps a definition of the but I agree that it doesn't look as if, I mean, on one side, the ambitwistor string is giving you supergravity amplitudes, and that you don't really expect the type 2 string theory, whatever definition you might give of its tensionless limit, to be just type 2 supergravity.
Yeah. Maybe this, I mean, perhaps that last sentence in that paragraph wasn't entirely clear. I could have maybe put another slide on this issue with the Gross-Mendel saddle point. That's the real argument, I think, because that's a very explicit calculation which shows you that they're actually not equivalent to each other. They give you different results.
Okay, all right, thanks.
Okay, so the reason if I can spend just a couple of minutes so sort of explaining why I think this result is interesting. The real reason why I think it's interesting, and this is the whole reason behind this project, is that this holomorphic chiral integrand, which I calculated, I can go into the details of the alpha prime corrections, but it was really just for record, just for purposes of knowing what they are. They sort of correct the ambitwistor string result at higher genus, the same way that we already know correction exists at genus 0. And this was a problem that was actually posed, I mean, sort of lightly posed in a paper that came out back in 2019. And so to really just provide the background for that, what's the whole field theory interest, or the field theory motivated interest behind looking at something like chiral splitting in superstring theory? Because the truth is that chiral splitting doesn't help you calculate very much in superstring theory. If you want to do higher genus calculations, even formally, you're going to have to triangulate the moduli space and then perform something called vertical integration, which manifestly destroys chiral splitting, because once you triangulate the moduli space, you don't have a complex structure. You can't split these in terms of holomorphic, anti-holomorphic pieces or anything. The real interest in chiral splitting comes from what we see in field theory, a specific phenomenon that we've observed for some theories, namely the double copy, which is expected to hold true perhaps to some order, mainly for supersymmetric theories. The double copy basically is the statement that for certain gravity theories and for a corresponding class of gauge theories, you can take gauge theory amplitudes and fuse them together in some bilinear fashion, and the result is an integral, a scattering amplitude or an integrand for the aforementioned gravitational theory. There are several manifestations of this. The most famous and the most precise, of course, is the KLT relation, which tells you that you can literally take two tree-level gauge theory amplitudes and fuse them using a kernel, and that gives you a gravity amplitude. But at tree level, this is equivalent to a less exact, but probably more general result, which is now named after Bern, Carrasco, and Johansen, which basically states that if you expand the integrand of a gravity theory in terms of trivalent diagrams, you present them in a form that in which each diagram is basically the product of two kinematic numerators, and for triplets of trivalent graphs, they obey the same Jacobi relations that color factors would obey, then you can map between gauge theory amplitudes and gravity amplitudes by simply replacing these kinematic factors by color factors, or the other way around. Now, Jacobi satisfying kinematic numerators at tree level, I mean, tree levels where the calculation has been done, but the result is true more generally, are now known to be obtained as a result of just performing residues on the ordinary moduli, the ordinary moduli space. I've only mentioned the tree level result because that's where the calculation has been done consistently so far. And the advantage of doing this at tree level until now is that we know that the alpha prime corrected Pfaffian at tree level is in a secret sense independent of alpha prime. That is, you put this on the support of the scattering equations, the alpha prime dependence drops out. So that's why you can comfortably take this gauge invariant Pfaffian that you've obtained from string theory, perform these residue calculations, and then obtain alpha prime independent kinematic numerators that automatically satisfy BCJ simply because of the global residue theorem. My hope was that these alpha prime corrected result for the RNS for higher genus might be relevant for doing this. So of course, proving this or establishing that this is relevant for proving the double copy requires us to do a calculation, which at the moment, I don't know whether or not we have the technology to do these calculations. We're going to have to put something like this, these expressions on the support of the scattering equations, and then see to what extent the alpha prime corrections drop out. Now, they manifestly drop out at genus 0. If you localize this on the if you localize the integral on the nodal Riemann sphere, like we do for the genus 1 ambitwistor string, you can show that the alpha prime corrections drop out in the same way they drop out for tree level. At genus 2, I don't know whether this is true, and I expect that at higher genus, the calculation has to be done in some local sense because of the existence of spurious singularities. At genus 2, and I can get into this if somebody's interested, spurious singularities don't show up because of some subtleties in the genus 2 calculation for the ambitwistor string, but there might be a complication of higher genus. So I think the real interest I had when I started working on this is to eventually see an application of this alpha prime corrected result to understanding to what extent we can push something like the double copy, because whether or not it's true, or because on some level I think the double copy really does descend from this chiral splitting procedure, and that's really why I was interested in this whole thing. Okay, so that's thank you, and if anybody has any questions, I'm happy to get into them.
Yeah, thanks for your talk. Just coming back on this, I'm not sure there's kind of two things that so that the older alpha prime corrections drop out at tree level, for instance, on the support of the scattering equations. That's because these higher order alpha prime corrections, they can be seen as coming from integration by parts.
Yeah.
Integration by part kills. Yeah. So that's one thing that's clear, and they drop out whether it's for bosonic or higher supersymmetric things like heterotic or something. But at the same time, it's also known that at finite alpha prime, that this chiral string has, for the bosonic string, has extra, like 2 extra states, right? It's this Siegel story. So when you compute the scattering amplitude, it has alpha prime dependent objects, which correspond to these massive ghost spin 2 states.
Oh, I see. Okay.
And these they drop out in the superversion because the spectrum is just, you know, it's just supergravity. So my question before was kind of related to this, whether these higher order alpha prime corrections in the superversion you're describing could drop out simply because there isn't alpha prime dependent states in the spectrum.
That it would be nice if they dropped out. I don't know, because I mean, to convince myself of this, I would have to perform the Genus 2 calculation, like putting them on the, by putting them on the support of the scattering equations. I don't know how to do that. So it would be interesting to see, but this is not something I've thought about.
Okay, thanks.
Yeah, I think Professor Loganayam has a question.
Yeah. Hello. Hi. Yeah. So if I may, like, you know, like just go back and ask another question. So here you're talking about, you know, like tensionless limit and trying to get it and so on. Now, of course, you know, like we kind of expect supergravity physically to be a good description when we have alpha prime going to 0, right? You know, like or infinite, when the string has infinite tension. Right? In some sense, in that limit is where we usually derive supergravity. So what is the relation between the two? Like, you know, like, I mean, there is a, I mean, this is always a kind of conceptual confusion, which I've always had with this kind of discussions, which is that, you know, like, yeah.
I'm sorry, are you saying that, I hope I got this right. Is it that supergravity is regarded as a good description for the tensionless limit in general? I don't know if that's true, because I mean, the tensionless limit is alpha prime goes to infinity.
Yes.
Alpha prime goes to 0 is, in string theory, you do expect that to be supergravity, so that's fine. But are you talking about the localization of the amplitude on, you know, these saddle points?
Maybe let me rephrase this question a bit and then try to make it a bit more precise. Is there a way to derive the ambitwistor string from, let's say, RNS formalism to be definite in the alpha prime going to 0 limit?
No, I'm sorry, could you please repeat that?
Do you think it is possible to derive something like ambitwistor string from the RNS formalism
in the tensionless limit?
In the alpha prime going to 0 limit, in the infinite tension?
In the alpha prime goes to 0. Yeah, so that's, I perhaps should have mentioned that in the beginning. I'm sorry. This was, there was a heuristic proof due to Mason and Skinner back in 2013 in the original ambitwistor string paper, where they claim to do this. So they take the Polyakov action and they take the alpha prime goes to 0 limit by rewriting it in terms of Lagrange multipliers and isolating out the pieces that depend on alpha prime. Then they're able to take the limit with relative ease, and what they get is the ambitwistor string action. But this was a heuristic at the level of the Polyakov action. What I've discussed in this slide is secretly the question that you're asking. Whether it is possible to actually prove this at the level of the integrals. It would amount to showing that each alpha prime dependent term in the expansion vanishes on the support of the scattering equations, since each of them is divergent as alpha prime goes to 0. So you would have to do some kind of integration by parts and check whether or not it's whether or not you get the supergravity result in alpha prime goes to 0 limit.
Yeah. So the hope is that somehow at the level of, you know, like the integrands and even more ambitious, even at the level of this moduli space integrals, you know, like this will work. That there is a sense in which you can take the full like a standard superstring theory, and at the worldsheet level, you can kind of take, like a supergravity limit.
Yeah, I mean that.
The hope.
Yeah, that's what I'm hoping will or will not be shown. See, either way it would be interesting, because if it's not true that you could take the alpha prime goes to zero limit and consistently get a result on the support of the scattering equations, that basically tells you that the double copy in some sense doesn't work beyond a certain genus order or for a certain number of particles, whichever is the problem. But of course, if it works, then I think it goes a relatively long way to understanding where the double copy comes from. Either way, the result would be interesting, but I think that's what it would boil down to, at least in the context of the ambitwistor string. But more generally, if you want to look at the alpha prime go to zero limit, I think there might be other ways of doing that by computing how the propagators change in that limit, rather than doing what I'm doing. I believe Piotr had a paper on this some time back, which I think might be a better way of doing that. So I hope did I answer your question?
Yes, sort of, yeah. Thank you.
Sure. Yeah.
Can I ask one more thing? Is somebody else?
Yeah. I think Alok has a question.
Yeah. Hi,
sorry,
Nikhil.
yes.
Yeah. So just about the last thing, so you're saying that basically the goal is to understand double copy when you include alpha prime corrections, right?
Yeah.
And so even at genus 0, you said. So I was just wondering, because there is, I guess you want something more general, but we do know that if we say from the field theory side, if you deform Yang-Mills by F cube higher derivative operator, then there is a double copy which produces the gravity amplitudes with higher derivative operators, right?
Okay, yeah.
So I don't know if you, is that an evidence in the favor of this, what you want to accomplish eventually?
Yeah, so at genus 0, things are very, quite simple on the gauge theory and the gravity side, because the double copy is true at a string theory level, not just at a field theory level.
Well, but at field theory, we don't know in general. I'm just saying that if we add higher derivative corrections, we don't know in general if it's true, the double copy is true.
Yeah, at the higher derivative.
But we have some evidence now that if we add, say, F cube term in Yang-Mills, then we can use double copy to generate gravity amplitudes.
Yeah, so I don't know which result you're specifically talking about, but it might, the F cube corrections are probably ones that come from are basically effective vertices that come from some string theory, probably the superstring.
Right. I was just talking in the field theory. So this is the recent work of Dixon and collaborators, right, where they show that there is a double copy for tree-level amplitude, even if you add this class of operators to Yang-Mills.
I see. Okay. Yeah. That it might. So you can do a lot of things at tree level. It's possible to express virtually any scattering amplitude as a CHY amplitude at tree level. So, the double copy is a little easier to discuss at tree level in general. But
well, sorry, I want to distinguish KLT from double copy, right? So BCJ, finding BCJ numerators, it's not obvious in field theory that even at tree level that if you add any high derivative operators, you have a BCJ representation. Right?
Yeah, but so long as you have a CHY representation, then it's always true, because you can always insert a complete set of states using your.
If you have CHY,
yeah, of course. That's what I'm saying. Okay. So long as you have and at tree level, it's always possible to find a CHY representation.
Okay, maybe I will ask you later. And then just one more quick question was maybe I misunderstood. You said that the difference between ambitwistor and RNS wash out at the integrand level?
At the integrand level, yeah. So long as you restrict yourself to the holomorphic sector.
Oh, I see. Because I thought the statement was that you have a double pole and you have to do integration by parts to wash out the differences, right? So you have to integrate to wash out the, maybe I misunderstood that.
I see. You're talking about tree level, I'm assuming, because that's.
Yeah, definitely at tree level. I don't know if this statement is true but that tree level statement required integration, I thought.
Because the statement you just said is true at tree level and one loop level. And the integration by parts is, it's a very straightforward way to see it. But it's important to remember that the integration by parts is true on a very specific locus in the moduli space. Now, at tree level, there's no problem in performing integration. So one should not consider that a handicap. But at genus 1, the statement I just made is true so long as you work on a specific locus of the moduli space, namely the one coming from the nodal Riemann surface. Now, once you have a nodal Riemann surface, you can perform integration.
I see. Okay.
So you do integration by parts on that part, then it's true. But a slightly more modern way of saying that is they belong to the same twisted cohomology class. So you can just shift them by some quantity proportional to the scattering equations, and the answer stays the same. So the alpha prime correction parts are they are pure gauge. You can just gauge them out by just shifting with the by some total derivative.
I see. Okay, thanks.
Can I ask a question?
Yeah.
So I guess the formulation of the theory shouldn't depend on the gauge slice. So the Beltrami differentials that you have been considering, have you been assuming they're holomorphic in the moduli?
Yes. Yeah. I'm sorry, by gauge slice.
So,
yeah, I'm sorry, by gauge
in
slice,
moduli space.
Yeah,
the parametrization, if you like, of the moduli space. The choice of Beltrami differential, essentially.
I see. Okay.
Okay. So,
yeah.
Just to elaborate a bit on that. So I guess it should also be possible to choose a smooth gauge slice, where you don't have a holomorphic dependence of the Beltrami differential on the moduli. In which case, you will, I guess, lose the chiral splitting, but you might gain something, which is the ability to go to arbitrary loop order.
Okay.
I think that might be interesting. I don't know to what extent smooth gauge slices have been looked into.
Okay, so
in this context,
the Beltrami differentials I've chosen is evaluation at a point, which I'm sorry, I don't think it's holomorphic.
So I guess, sorry, one sec. Are you sure? I mean, in order to have the chiral splitting.
No, I'm sorry.
You
Just
have Beltrami times
right.
ghost.
No, right. You're correct. They were holomorphic. Yeah.
Yeah. So more generally, you would have Beltrami. Let's call it mu b.
Yeah.
B is the B ghost or the super field ghost B, plus the antichiral half.
Yes.
Right. In general, you have Beltrami B plus antichiral half. So if you allow for antichiral half, if you allow for smooth dependence of mu essentially on the moduli, then there shouldn't be an obstruction of the Donaghy-Witten type. And then one should be able to make more general statements, but one will lose the holomorphicity, the chiral splitting of D'Hoker and Phong. Of course, that won't hold anymore. But I don't think that, I mean, that shouldn't be a problem. But this also indicates that the formulation of the theory, maybe the holomorphicity is not as fundamental as.
Oh yeah.
Maybe,
no, yeah, that's something which I mean, I've been convinced of that earlier as well when I've talked to people who work in actually computing in serious superstring amplitudes. I've been told that chiral splitting is not really valuable if you want to do calculations, because I mean, even more simply, if you want to perform something like vertical integration, you lose chiral splitting even if you have it to begin with.
Yeah.
And with what you're saying, it might be interesting to see if you can find a global smooth splitting. Is it
in fact, you won't even need vertical integration.
I mean, is there a global smooth splitting or is there a global smooth projection?
Yeah, I think I don't really know the difference between the two, but I think the answer is yes.
I see. Okay.
Is there a difference? I mean, what is the difference between smooth splitting and smooth projection?
Well, with splitting, I think I know what a splitting is, and I guess anything that's not a splitting you would call the projection. A splitting is just when you can choose a class of coordinates such that the super manifold is just a bosonic manifold along with a collection of Grassmann coordinates. So it's just a trivial Grassmann integral that brings you from one to the other.
So the transition functions on patch overlaps.
Yes.
The bosonic ones, do they only depend on bosonic?
Yes, I think so. Yeah.
Yeah, and the fermionic ones are proportional, are just first order, degree.
Our first order in the Grassmann variables.
Right. So that's what you mean by a holomorphic splitting or holomorphic projection.
That's a holomorphic splitting.
Okay, so what's the holomorphic projection in terms of the transition functions?
I think they can depend super holomorphically on each other, but I don't think you can just resolve the bosonic and the fermionic pieces. But you can patch them together in a holomorphic way, I think. This
okay,
is
so what I'm
possible
referring to
for-
is the transition functions. Yeah, can be patched together in a superconformal.
I see. Okay.
Wait a minute. The Riemann set, the super Riemann sets can be patched together using superconformal transition functions.
Okay.
In all cases, even for smooth dependence on moduli or the Beltrami differentials.
Yeah, I mean, isn't that the obstruction of Donaghy and Witten, that you can't patch them together in a super I think the obstruction you can't patch them together in a holomorphic fashion. I mean, keeping the two pieces distinct, the fermionic and the bosonic pieces.
Yeah, so I
maybe
don't know.
maybe what you're saying actually
but
mixes them together. Maybe that's the problem.
I think what I'm saying, I don't understand this in as much detail as I would like, but I think what I'm saying is that at fixed complex structure, you have a super Riemann surface at fixed complex structure, and on this fixed complex structure super Riemann surface, you have superconformal transition functions. Okay, you can break it up into patches, and on patch overlaps you have superconformal transition functions and co-cycle relations and so on.
Okay.
Now, when you deform the moduli, the patches you can think of deforming the moduli as shifting patches, the patches that you originally define your fixed complex structure super Riemann surface. So if you shift the base points of these patches in a smooth way, you see that generates the moduli deformations in a smooth way, but it preserves the superconformal transition functions on any for a fixed complex structure. I'm probably not. I don't know to what extent I'm explaining myself clearly.
Yeah, I mean,
it's a little. Of course, it's a subtle thing, but
what I wonder when I hear something like this is how different something like this actually is from vertical integration.
Yeah, so vertical integration you can do with just holomorphic. You don't need to go to smooth.
Yeah, right. Because you
description, right?
But you lose holomorphicity when you actually perform it, because you have to
you have
to move these PCOs in a very clever way.
Yes.
Make sure you don't touch these spurious singularities when you perform the
Yes. The advantage of the smooth.
What you're saying sounds very similar to this.
Yeah, but you don't actually need to these vertical integration. You can interpolate smoothly throughout the moduli space.
Okay.
At least this is. I mean,
I don't know if vertical integration is something that isn't smooth.
I don't think
it certainly isn't. It certainly isn't holomorphic.
So on patch overlaps, you have holomorphic dependence, right?
Yes.
And then you glue together on patch overlaps using this jump.
Yes. Yeah.
Yeah. So instead of having a jump, you can allow the transition function to be smooth throughout. You don't.
Oh, I see. Okay.
You see what I mean? Yeah. I mean, I don't think this has been worked out. I mean, unless it has, and I don't know about it. But
do you think this is a way to sort of determine a manner of integration over the moduli space?
Yeah.
Intrinsically from the supermoduli space. So in the paper that Witten and Sen wrote, they say that you would expect something like vertical integration simply from the structure of the supermoduli space, because if you have a bunch of patches there and you define integration using a partition of unity, on each of the patches you have a projection down to the ordinary moduli space, and you take this partition of unity and then you sort of project that expression down to the ordinary moduli space. In the overlaps, you would have to perform some kind of correction, and that's really what vertical integration in a very special way is doing. So what you're saying sounds like a more general way of doing vertical integration.
Yeah. So that vertical integration depends on a choice.
Yes.
What I'm saying is that you don't need to make that choice.
Yeah, exactly. Yeah. I mean, what you're saying, I believe, is not in the literature already.
Yeah, I don't think it exists.
It might be.
Yeah, that's true.
I know someone who would like to work this out, so it would be nice.
Yeah,
I know there are people who would like to work this out. So
yeah. So I've been thinking about it a little bit as well, but yeah, it's an interesting question, I think.
Right.
Hi, I just had a sort of a little bit of a vague question, which is, so if I understood correctly, you were looking at the integrands and arbitrary genus, and then you got the chiral piece of the superstring is sort of the half of the ambitwistor integrand, but I was wondering whether this suggests that you could do something at the level of the action in some ways, and try to. I mean, if this is true genus by genus, you would think that the underlying reason for something like this would be by being able to rewrite. I mean, being able to show this at the level of the functional integral before doing the integral in some way, perhaps, and the fact that the ambitwistor string is sort of localized suggests that you might want to see some kind of you might want to write the integral the path integral as some as a sort of a Q exact piece, as a kind of a topological string, and that the alpha prime deformation or 1 over alpha prime deformation, the tension deformation, is some sort of a Q exact quantity. That's often how it works in topological string theory, and sort of would, in a way, go towards what Loga was asking in some way, that the alpha prime deformation is a sort of a Q exact thing, and therefore it doesn't really matter, and it's like the usual arguments about Witten index and so on, that you can evaluate it at t equals to 0 or t equals to infinity, but it doesn't really matter.
It doesn't really matter, yeah. So
I was wondering whether you had thought of something of this level, of this kind, at the level of the functional integral.
Yeah. So I mean, this, if we're restricting attention to the ambitwistor string, and I assume we are, what this is basically saying that if the ambitwistor string is given by some topological action or some twistor string approach, and it's manifestly alpha prime independent, and you deform it in some, and I'm assuming the BRST operator is the one coming from the ambitwistor string, and we deform by alpha prime using this BRST operator. This is the same as saying that you're at the level of the amplitudes, you're deforming all the integrands by something that's proportional to the scattering equation, or proportional to the scattering equations. So this particular way of framing this question is the same as saying that, or establishing that all of these alpha prime corrections vanish when you integrate them over these Grossman-Day saddle points.
But I wanted to see it sort of happen not at an explicit level, but at a sort of a level of as a deformation of the action.
So if this can be shown, I mean, I was generally distrustful of ways of directly working at the level of the action, since a lot of the calculations seem like tricks to me. But this, if something like this could be shown, I think it would be, it would be convincing as a proof of alpha prime independence, which is the main point of all of this. So if all of these amplitudes could be extracted from the ambitwistor string by showing that all you have to do is deform it by some BRST exact part, then I think that would work as a proof of alpha prime independence without having to do all these calculations that I've done. Yeah.
Right.
I've not thought of it, but that's probably a better way of phrasing this whole thing.
But more specifically, that's one outcome which would, of course, be desirable and would be very illuminating. But just as a sort of a lesser outcome or a first step, just understanding whether, I mean, you are taking a very well-defined alpha prime goes to infinity limit at the level of the integrands of the chiral, in the chirally split superstring, the RNS superstring, right?
Yes.
Whether you can just see that deformation, I mean, that 1 over alpha prime write it in a way such that, you know, the leading piece, write the functional integral of sort of which, try to split the functional integral into the chiral and the two chiral pieces, and then see whether each of them can be viewed as a piece which is effectively giving the ambitwistor action, and then something which is the 1/alpha prime correction. And then, of course, you can try to see that that 1/alpha prime correction is a Q-exact thing, and so on, and move towards the second goal. But I just at the level of the integrands, I mean, so what you've seen at the level of the integrands, whether you can see at the level of the functional integral is sort of my general thrust. And then, yeah, so this part is independent of whether or not it's a topological string theory or Q-exactness or anything. It's just a statement of what you have already shown to understand that in a more from a sort of a more from a deformation point of view.
I see. What you're saying is it might be possible after performing the x integrals, but before performing the psi integrals, since the alpha prime structure becomes evident at that stage of the calculation. So at that point, it might be possible. Yeah, the answer is also quite simple at that stage before you perform the psi integral. It's not so unilluminating at that point. It becomes very complicated after that.
Yeah, so some kind of an auxiliary, so you sort of, perhaps do, like in any functional integral manipulation, you sort of perhaps integrate out some set of the fields and then work with an auxiliary set of, maybe introduce some auxiliary fields and work with a sort of an equivalent action, but in which the 1/alpha prime deformation is a very explicit deformation. Is a very explicit understand, so that the leading piece which you can manifestly maybe make it agree with the Mason-Skinner kind of action. I mean, they also have some kind of a chiral action, right? So or some reworking of that action or some other this thing, so that you can make them both agree. And then the other one that you're getting from the RNS superstring has explicit 1/alpha prime deformations.
Right, yeah. I had not thought of this, but yeah, this would probably be a better way of going about proving alpha prime independence. Yeah.
Okay, thanks. Thanks for a nice talk.
Yeah.
Any more questions? Okay, if not, let's thank Nikhil once again for this nice talk, and we'll see you guys next time.
Thank you very much.
Thanks, Nikhil.